Should be in. Oh, there you go. Okay, so now we're live online. So let me welcome everybody once again. Sorry for the 30 seconds or so delay that I think is happening. To the online SPICE-SPIN+X seminar series, sponsored by Spin Phenomenon Interdisciplinary Center that I run together with Karen Eversocete, now also Jamir Marino, and in collaboration with the SPIN+X Collaborative Research Center that is from between Kaiserslautern and Mainz, led by Martina Schliemann, Burkhard Hillebrands, and Matthias Chloe here in Mainz. Just to keep everybody in reminder that this is a Zoom web seminar, that you'll hear the speaker and the person speaking, but then please enter your questions during the talk, and I will give you the microphone afterwards. And then to just simply let me know, also raise your hand and I can pass the microphone. As usual, we have every Wednesday, we have the talks. I think next one is from Christian Bach. And today is a pleasure to welcome Henning Sirringhaus, as a very well-known person in the charge transport and photo and photoelectric devices in polymer systems, in organic systems, as organic semiconductors and hybrid systems, doing fabulous work in Cambridge, with which I have the pleasure to have had worked for the last 5-6 years in a synergy grant. With that, I think I will just give the floor. I'll stop sharing, and please, Henning, go ahead and start sharing your screen. Okay, can you go ahead and start sharing your screen and your presentation, Henning?
Yes.
Okay.
Can you see this?
Yeah.
Looks great.
Perfect.
Great.
Great. Go ahead.
Thank you so much, Jairo, for the very kind introduction and also for the invitation to speak. It's a really great pleasure for me to be here. It's a great distraction from the kind of lockdown life that we are leading. Unfortunately, I can't see you all, but I hope I've got some interesting presentation for you. I understand you are a kind of relatively general audience. So my aim in this talk is to introduce how we understand the charge and spin transport physics of organic semiconductors. And I hope it's kind of giving you a little bit of feeling for how unique and how different the physics of these materials is to the physics that you might know from conventional inorganic semiconductors. So the materials that I don't seem to be able to.
Sometimes you may want to restart it then.
Yes, I might have to restart. Sorry for this. Oh yeah, it's working now.
It's working.
So this is a little cartoon of an organic semiconductor. So this is a pi conjugated molecular system where you have essentially electrons that are in pi molecular orbitals delocalized over the molecule. And what we are interested in is understanding kind of the charge transport physics, the optical physics of these pi electron systems. And it's a field that has a very close link between physics and chemistry. And so the chemists, of course, are able to make a whole range of these conjugated molecular structures. You can arrange these pi conjugated molecules in different ways. You can introduce heteroatoms, and that's an incredible versatility there. And so by exploring the structure property relationships, trying to understand how particular molecular structures impact physical properties, that's what is driving this field forward. It's driving certainly improvements in device performance. So what you can see in the middle slide here is how the figure of merit of one of these organic devices that I'll talk about, a field effect transistor, which is the field effect mobility, how it has improved over the last 20 years or 20 to 30 years. And so what you can see is that there's been really quite phenomenal progress in improvement of materials properties, going from mobilities that used to be very, very low, 10 to the minus 3, 10 to the minus 4 centimeters squared per volt second. And now we have organic semiconductors that have mobilities, not huge mobilities compared to graphene or the best inorganic crystals, but we have organic semiconductors that have mobilities between 1 and 10 and some approaching 20. And that's, of course, what I want to talk about in this talk, how we understand that in terms of the physics, what physics is responsible for that. But before I do that, let me talk a little bit about applications. Of course, that's useful background. And there is a field of semiconductor technology emerging that uses these organic semiconductors as the kind of key semiconducting material. You're probably familiar with organic light emitting diodes, where there's lots of TV displays and mobile phone displays that use organic semiconductors as the light emitting diode elements on the different pixels of the display. There is a whole effort to realize organic solar cells, organic photovoltaics. That's not quite as mature commercially as the organic LED displays, because the efficiency of organic solar cells is currently, has also improved greatly. It's now currently about 18%. Power conversion efficiency. That's still a little bit lower than what you get with silicon. Silicon is around 20–25%, but it's certainly an interesting future application for these materials. There's a lot of interest in using some of the mechanical properties, the flexibility and stretchability of organic semiconductors in bioelectronics, integrating electronic functions onto human skin. There's a paper here that you might find relevant, or maybe even implanting electronic devices into the body, or into interfacing directly with nerves. It's a whole field that's emerging there. And then the field that I'm most closely interested in is the field of flexible electronics, where we use these organic semiconductors as electronic switches, electronic devices, for example, to drive displays. So what you can see here are flexible liquid crystal displays, video displays that are not driven by amorphous silicon transistors, but by a backplane of organic transistors. And as I said before, I mean, this is not necessarily driven by kind of organic semiconductors having completely outstanding transport properties. I mean, as I said, the field effect mobility of an organic transistor typically has mobilities between 1 and 10 centimeters squared per volt second, and that's lower than the kind of best inorganic thin film electronics technologies. It's better than amorphous silicon, which is the material that's currently used, but some of the more advanced inorganic semiconductor technologies like polycrystalline silicon or oxide transistors have better mobilities. But what the organics have going for them is the kind of ease of processing. You can process them pretty much at room temperature or below 100 degrees C. That enables you to work on flexible substrates. And then, of course, also the mechanical properties. Some of these organic materials, at least when they are in polymeric form, they are highly mechanically flexible, and that allows you then to integrate electronics in new form factors. And those properties are the ones which are driving the technological adoption. So much for applications. As I said, it's a physics talk, so I don't really want to go much further there. I now want to kind of talk a little bit about the different types of organic semiconductors, and there's essentially two different material systems. There are what we call small molecule semiconductors, and you can see some examples of that on the top of this diagram here. It's essentially small conjugated units where you have these fused benzene-like rings. Sometimes you have these flexible side chains attached to the periphery, and that helps to induce the solution processability of these materials. But these small molecule systems are typically highly ordered polycrystalline materials. You can grow single crystals and achieve fairly high carrier mobilities in, as I said, on the order of 10 centimeters squared per volt second. And then the second class of system are the conjugated polymers. They are long chain polymeric pi systems, and traditionally they used to have much lower mobilities than molecular systems, just because in a polymeric system you tend to have much less ordered structures, more amorphous microstructures. But there have been recent developments that have brought the mobility of polymeric systems up almost to the level of the small molecule systems, and we now have quite high performance polymeric systems with mobilities in the range between 1 and 5 centimeters squared per volt second. And from a technological perspective, polymeric systems have their advantages because they are easier to process. You can achieve higher uniformity over large areas. But it's also true, because of these different microstructures, polycrystalline versus more disordered structures, the physics of transport is likely to be different. And that's why in this talk, I first want to talk about small molecule systems. And then in the latter part of the talk, I'll briefly talk about the physics of transport in polymeric systems. So in order to introduce this, let me start right at the beginning, the electronic structure of an organic semiconductor. So on the left-hand side, you can see the energy level diagram of the simplest conjugated molecule, or one of the simplest conjugated molecule, called benzene. It's probably something that you've covered in your undergraduate or high school chemistry courses. So what you see here are the different molecular orbitals of benzene, and there is a highest occupied molecular orbital and a lowest unoccupied molecular orbital. And these are the ones that essentially form these. I mean, these are the pi electron states that we are talking about here. So the HOMO, the highest occupied molecular orbital, is essentially the valence band of these semiconductors. And the LUMO, the lowest unoccupied molecular orbital, provides the conduction band. Of course, it becomes more complicated when you then have more extended pi systems, and when you have a solid where you have different molecules bonded together, not by covalent bonding, but by weak van der Waals interactions. But if you are an inorganic semiconductor physicist, you might look at these molecules they might not look too dissimilar to you than a covalently bonded semiconductor like silicon. So here you've got a picture of the crystal structure of one of these conjugated molecules, this 5-fused benzene ring here, this molecule we call pentacene. And you can form single crystals of pentacene. And typically the molecules in the single crystalline structure arrange in a layered fashion, where within the conjugated layers you have this characteristic herringbone stacking. You're looking at the molecule here along the long molecular axis, so it's a projection along the long molecular axis, and you can see how these individual molecules, they stack with respect to each other in this characteristic herringbone stacking. But it's essentially a periodic arrangement of molecules, and you can think of that similarly to a periodic arrangement of atoms, and you can define Bloch states that are derived not from atomic orbitals, but in this case from those pi molecular orbitals similar to those of the individual benzene rings. And then you can think of a band structure forming. And on the bottom right, you can see the calculated band structure of pentacene. And what you immediately notice is, of course, that this doesn't look like the band structure of silicon. And the main difference is that the bands are really flat. They don't go, the band dispersion is not several electron volts, but only on the order of maybe half an electron volt as you go across the Brillouin zone. And the reason for that is, of course, that these molecules in the solid state are relatively far apart from each other. The typical intermolecular distances, the pi-pi stacking distances, are on the order of 3 to 4 angstrom. And if you calculate the transfer integrals that appear in the Hamiltonian and mediate the hopping from molecule to molecule, they of course depend exponentially on the molecular distances. And for these spacings of 3.5 to 4 angstroms, you get transfer integrals on the order of maybe a few hundred milli-electron volts. And that's the reason why these bands are relatively flat. But in principle, that's maybe the starting point for understanding the electronic structure of such a molecular crystal. And so experimentalists have then, looked at the transport properties of these molecular crystals. And on this slide, I show you a few of the key characteristics that you typically observe when you're studying transport in these molecular systems. On the top left, you can see the temperature dependence of the mobility in one of the most widely studied molecular crystals called rubrene. And what you see there is that the room temperature mobility is on the order of 10 or 20. And as you then cool down, the mobility increases slightly and reaches a maximum around 200 Kelvin before it then drops sharply to lower temperatures. This sharp drop to lower temperature is an effect of residual trapping. There are some defect states that tend to, shallow trap states that tend to trap these carriers, but up to 200 Kelvin, you're essentially seeing the intrinsic band-like temperature dependence of the mobility, which is somewhat similar to that of silicon. It's essentially, as you cool down, there is fewer scattering events with phonons. That's how you would interpret this in silicon. So that looks a bit like band-like transport in silicon. And also, if you measure Hall effect, you can measure very clean ideal Hall effects in these systems where the Hall resistance is inversely proportional to the carrier concentration. So that also is a very clean semiconducting transport. But then there are also other aspects of the physics of transport that are a little bit more peculiar. We have worked in our group a lot on the optics of charges in these materials. So if you induce carriers into an organic semiconductor and look at what optical absorption these charge carriers have, what you typically see is a very characteristic sub-band gap absorptions in the infrared that are characteristic for these charge carriers. And what's quite strange is that these optical absorptions, they look very similar in many cases to what you would see if you were dissolving these molecules in a solvent, so completely isolating them, and then charge them chemically. You can then extract an electron, let's say, by some chemical doping process, and then look at that charged molecule in solution. And these absorption spectra that you measure in the solid state, they look very similar to the ones in solution, which tells you that probably we are not talking about completely delocalized Bloch electrons here, but we are talking about electronic states that are more localized, maybe not to individual molecules, but to a small number of molecules. And you also see other peculiar features. For example, this is a very beautiful recent paper from Vitaly Podzorov's group at Rutgers, who looked at the modulation of the mobility with mechanical strain. Because these are flexible materials, you can form the devices on flexible substrate. You can apply mechanical strain quite easily by bending the substrate. And what you see there is that the mobility is very sensitive to strain. Just a few tenths of % of strain, you can increase the mobility by almost a factor of half. And that's something, if you analyze that quantitatively, it's not something that's expected within band theory. The effective masses or so, they don't change that much when you apply this little bit of strain. So that's a little bit an unusual feature that requires explanation. And one of the key features that is really governing the transport physics of these molecular systems is the structural dynamics. And so this is some transmission electron diffraction pattern that you see here on the left. Is some study that we've undertook a few years ago, where we were trying to investigate the single crystal structure of this particular molecule that you see in the middle here. And you can see these sharp diffraction spots that indicate the crystalline molecular lattice, but you also see these diffuse streaks very pronounced in the diffraction pattern. And it turns out that these diffuse streaks are manifestations of fairly strong thermal lattice fluctuations. So at room temperature, the molecules are fairly strongly vibrating around their equilibrium lattice positions, because the bonding, of course, in these materials is soft. It's not a covalent bonding, but van der Waals bonding. So the molecular vibration amplitudes tend to be relatively large. And we developed, in fact, a technique using these diffraction patterns to quantify the vibrational amplitudes. And you can see that on the right-hand side here. At room temperature, the molecules vibrate against each other. Neighboring molecules in the unit cell, they vibrate against each other with amplitudes on the order of a few tenths of an angstrom. You could ask yourself whether that's a lot or whether that's not very relevant. And to answer that question, you need to ask yourself, how much do the transfer integrals, how sensitive are the transfer integrals to these relative fluctuations in molecular positions? And you can see that on the bottom right. This is a calculation of the transfer integral of two acene molecules that are basically shifted against each other along their long molecular axis. So if you calculate the transfer integral as you slide the two molecules alongside each other, what you can see there is that these transfer integrals vary very strongly with relative position. The sign changes. There are points where the transfer integrals are 0. There are points where the transfer integral goes through maxima or minima. So if you imagine now that in a solid system at room temperature, the molecules are all vibrating with a few tenths of an angstrom amplitude, this means essentially that all the transfer integrals are fluctuating strongly with those molecular vibrations. And it's this dynamic disorder in the transfer integrals that is the key to understanding the transport physics of these molecular systems. And based on this assumption or this hypothesis, there's been a theoretical model developed for these molecular systems that's called transient localization theory. It was developed by two theoretical groups, Alessandro Troisi, who is now in Liverpool, and Simone Frattini at Grenoble in France. And the picture is essentially that you have the molecules, if you induce a charge into a molecular lattice, this charge sees a dynamically fluctuating environment of transfer integrals. The Hamiltonian has not static transfer integrals as you might assume in a more covalently bonded system, but the Hamiltonian has all these temporarily fluctuating transfer integrals. And that leads to a localization of the charge carrier. At a particular point in time, the charge localizes within that disordered environment of transfer integrals. But then on a picosecond time scale or so, the molecular lattice evolves, and that leads to a motion or a diffusive motion of the molecular wave function within that dynamically disordered molecular environment. And so you can essentially think of the electron wave function surfing on the waves of molecular lattice distortion. You can see a beautiful visualization of this calculation here on the right-hand side, where you have I think it's a pentacene lattice again, where you at time t equals 0 localize the carrier at this particular point here in the lattice. This colored spot here indicates the molecular wave function highly localized at that point. And then you can basically follow it as a function of time. And you can see here that after 25 femtosecond, the wave function is much more delocalized over a cluster of maybe hundreds or almost 100 molecules in this case. And then 39 femtoseconds, a little bit later, the wave function is again more localized, but it's no longer at the point here, the origin, but it has diffused by a distance, some distance. And this diffusive motion that's in a sense driven by the structural dynamics, by the molecular lattice distortions, that is the process that governs the mobility. So you can express the mobility in this form here. The mobility is dependent on two key quantities. One is the so-called delocalization length L, which is essentially the characteristic length scale over which the wave function is able to delocalize at a particular moment in time. And omega naught here is the vibrational frequency. So essentially, this is a diffusive process where every time step is determined by the characteristic vibrational frequency. Every time step, the wave function hops by a length scale L. And that is how we understand carrier mobilities in these systems. And so then, of course, the difficulty is to understand now, is this framework suitable for understanding the differences between molecular systems. I've got here a list of some widely studied molecular semiconductors. As I said, rubin is one of the highest mobility systems with mobilities of 20. And then you have a few other systems that have been widely studied because of their high mobilities. And do we have a model that actually explains these differences? And the answer is yes. This transient localization framework is actually able to relatively quantitatively predict mobilities nowadays. You need to take into account a few more details that I haven't spoken about so far. One of the characteristics that's very important is how isotropic the transfer integrals are. So of course the transfer integrals, they calculate between pairs of molecules. It depends, of course, in which direction of the unit cell you go. So there are typically 3 different transfer integrals, JA, JB, JC, corresponding to different directions in the unit cell. And what you want so these are transfer integrals within the 2-dimensional pi-stacked planes. Of course, as I said, the molecules have this layered structure. In the 3rd direction, the transfer integrals are usually very small, and that's not what we're talking about here. We're talking about the transfer integral in these herringbone-packed conjugated planes. And what you want is that essentially the distribution JA, JB, JC is as isotropic as possible. That gives you the highest carrier mobilities. You also need to worry, of course, about how large these thermal disorder effects are. You want the fluctuations of transfer integrals to be as small as possible, or the relative fluctuation with respect to the size of the transfer integral itself. You want that to be as small as possible. And then, of course, the mobility also depends on the characteristic molecular vibration frequency. You want these to be as stiff as possible. And if you can compute all these quantities, and if you do that in the right way, then you can actually relatively quantitatively predict charge carrier mobilities. And you can see that here on the plot here on the right-hand side. There is a fairly good correlation between the theoretically predicted mobility within this framework and the experimentally observed mobility in single crystals. So that's the kind of the general framework that we use to understand charge transport in these systems. I now want to spend a few moments to talk a bit more about the details. Of course, I don't want to mislead you and give you the impression that it's all fairly easy and simple. It's actually quite complicated if you look at it in detail, because, well, the structural dynamics of these systems is actually quite complicated, because we typically have very complicated unit cells. The molecular systems, they have often 100 atoms in the unit cell. So that means there must be 100 phonon modes or several hundred phonon modes. And so effectively, you'd have to worry about what contribution each of the phonon mode makes to this dynamic disorder. Each phonon mode will lead to fluctuations in the transfer integral, and you might wonder about which ones are the ones that are most strongly affecting the transport. And we've recently done a detailed study of this in a series of molecular systems. You need some way to measure these molecular modes, and we used, in this case, terahertz spectroscopy, optical spectroscopy, combined with inelastic neutron scattering. And here you can see a summary of the vibration spectra of these different molecules. I don't want you to focus on the details, but a few points that I want to make. In the terahertz spectra on the left, you can see the lowest molecular frequencies, and you can see here that there are some really soft modes. This is not even the softest mode. The softest modes sometimes are around 10 or even less than 10 wave numbers. And so these are often intermolecular modes where molecules slide against each other with relatively soft coupling. And then you have many, many modes, these hundreds of modes. In the neutron spectra here, you can see them as you go to higher frequency. Of course, they acquire a more intramolecular character. The carbon-carbon stretch vibrations, they appear at higher frequency here. But essentially, you'd have to take all these modes into account if you want to understand how the thermal disorder is generated in these systems. We can describe these modes very well with density functional theory, high-level DFT, and then we can essentially do a mode-by-mode analysis of the electron-phonon coupling. So you typically start with these individual modes, this comparison here of two different molecules, DNTT, I showed a picture of that in the previous slide, and then it's an alkyl substituted DNTT where you have essentially two alkyl side chains substituted to the end of the molecule. And you can see here these different modes. The x-axis here is a frequency axis, and the y-axis is the amplitude. You can see that the lowest frequency modes have the highest amplitudes, and then they decrease, the amplitude decreases to higher frequencies. And then for each of these modes, we can analyze the electron-phonon coupling. The electron-phonon coupling is essentially the derivative of the transfer integrals with the normal mode coordinate. It tells you how much the transfer integral in a particular direction is modulated by that particular normal mode. And then the thermal disorder that's created as a result, the thermal disorder in the transfer integral in particular, is then in a sense the product of electron-phonon coupling times amplitude. And you can see this here at the bottom in a cumulative plot where this is the total thermal disorder that's present in this system, built up as we go from low frequency to high frequency and take into account the contributions of these individual modes. And so what you can see, something that was striking that we hadn't expected is that actually this histogram builds up in some cases in a rather step-like fashion. There are some modes that make a huge contribution to the thermal disorder, and there are many modes that make only very small contributions to the thermal disorder. So for example, in the C8-DNTT system that you see on the right, there is this first mode here, the softest mode, which generates almost 70% of the thermal disorder. And then all these other hundreds of modes to generate only another 30%. So we call these modes now killer modes because they're clearly the most important mode. There are some modes that are really generating a lot of the thermal disorder, and they are the ones that we need to particularly worry about if we're trying to minimize the thermal disorder and maybe maximize carrier mobilities. And these softest modes, that we particularly worry about now, are often intermolecular modes. And here you can see a visualization of this particular mode that causes the large disorder in this system. And it's a sliding motion where neighboring molecules slide against each other in the unit cell. Okay, so I hope that gives you a little bit of an impression on kind of the complexity of that you need to, if you really want to understand transport quantitatively, you really need to understand this dynamic disorder mode by mode and how it affects the transport properties. So I would like to summarize this first part of the talk by saying that the charge transport physics of this molecular system is governed by this close coupling between charge and structural dynamics. And in the last 2 or 3 years, this framework of transient localization has really gained acceptance in the scientific community as the most appropriate framework for describing the unique charge transport physics of these molecular systems. I now want to just briefly mention that, of course, we are not just interested in my group, we are not just interested in charge transport, but we're also interested in other transport coefficients in these systems. And so one thing that we've been recently very interested in is the thermoelectric properties of organic semiconductors. And here I show you an example of measurements of the thermal conductivity of these two semiconductors that I just spoke about, DNTT and C8-DNTT. And you can see here the thermal conductivity measured using this so-called 3 omega technique It's a measurement that measures the thermal conductivity in the plane of the film, in the plane of these herringbone stacked molecules. And what's quite interesting here is that the DNTT molecule, the unsubstituted molecule, has a thermal conductivity at room temperature of about 0.2 watts per meter Kelvin, which is already a low value. But then when we go to the substituted molecule, the alkyl substitution leads to a quite dramatic suppression of the thermal conductivity, and we are able to achieve thermal conductivities on the order of 0.05 watts per meter Kelvin. That's a really, really low number. If you install cavity wall insulation in your home, the best you can do is probably, the best thermal insulation materials that you can money can buy have thermal conductivities of a similar magnitude. So that's of course very interesting for thermoelectric properties, because for thermoelectrics you want materials with very low thermal conductivity. So we're very interested in exploring molecules like this for thermoelectric applications. And we're also starting to understand the reasons for that, because theory is again very useful in understanding the reasons for this low thermal conductivity. And it turns out that essentially what happens here is that the so-called participation ratio, which is a measure of how delocalized the normal modes are, is actually reducing significantly when you substitute with the alkyl chains. So the unsubstituted molecule has more delocalized phonon modes, whereas the attachment of side chain suppresses this delocalization, and the phonon modes become significantly more localized, and as a result the thermal conductivity is reduced. As I said, I just wanted to mention that in passing, that we're also interested in thermal properties. And then the third area that my group is investigating is the kind of spin transport in these molecules. And I show you here an example of a very simple but elegant measurement to investigate kind of spin injection into organic semiconductors. So we have here an interface between a ferromagnetic system, permalloy, and we deposit this organic semiconductor. Again, the same molecule, DNTT, is then deposited on top of the ferromagnetic surface. This is an experiment that was done by my PhD student, Angela Wittmann, at the time. And she then studied the ferromagnetic resonance properties of this ferromagnet with and without the organic semiconductor present. And if you compare the line widths of the ferromagnetic resonance before and after the deposition of the organic material, you can see a small broadening of the line width once you deposit the organic molecule, which indicates that there is some spin injection from the ferromagnet into the organic semiconductor. And we were able to analyze the magnitude of this spin injection, or the broadening of the ferromagnetic resonance, as a function of the interface structure. So you can deposit the neat molecule, and that gives you in fact the largest broadening, because this molecule is then in very close contact with the interface. But if you deposit this alkyl substituted molecule with this alkyl side chain, which are electronically, of course, inactive, they are insulating. And if you have such a monolayer of insulating side chain at the interface, that suppresses the spin injection very effectively, and we weren't able to detect any line width broadening in that system. And from these measurements, you can do these measurements as a function of thickness, and you can then determine the spin diffusion length in the organic semiconductor, and you get values of a few tens of nanometers. So this is just a kind of, a fundamental interest in understanding also spin transport in these materials. But I now want to kind of come back to the charge transport and focus on the other system that I mentioned right at the beginning, which is the polymeric systems. And polymeric systems are much more complicated because their microstructure is really much more complex. So you typically don't have single crystalline structures, but you have more heterogeneous systems where you might have some crystalline domains, where you these orange regions here, where the polymeric chains are packed together rather well and in a more ordered fashion. But then you have also these more disordered regions, these more amorphous boundaries in between these crystalline domains that are more complicated and where there is more structural disorder. And for many years, as I said, the transport physics of polymeric systems was completely governed by the energetic disorder that is present in such heterogeneous structures. Not every polymer chain is in the same molecular environment, and that means that the energies, the site energies, are distributed in a kind of distribution, Gaussian distribution typically. And this broadening of the density of states due to structural disorder used to dominate the charge transport physics of organic systems. But in the last few years, there's been a lot of progress, as I mentioned, and our group, as well as other groups, they have discovered polymeric systems where this energetic disorder is quite small. The main reason for that is that we've been able to make systems that have very well-defined chain conformations. So this is a kind of example here of a system that we call IDTBT. It's this polymeric system here. And in a solid state, although the chains are not single crystalline, they are relatively poorly ordered in terms of their direction and orientation. But the local conformation of the backbone, if you look at this, is a particular chain picked out of this ensemble, and you follow basically the molecular orientation along this chain, you can see that it's pretty much planar. There is no torsional defects. If there were torsional defects, you would see that in this projection. There's essentially a planar graphene-like nanoribbon that meanders gently as you go along the polymer chain. And because of this lack of torsional defects, the energetic disorder in these polymeric system is now quite low. We see that, for example, in the optical absorption, the Urbach energy of some of these polymers, it tends to be on the order of 20-25 millielectron volts, which is about the same as what you would have in a gallium nitride crystal, in inorganic gallium nitride crystal. So it's quite astonishing that despite this structural disorder that you have in these systems, you can make such energetically and electronically clean polymeric systems. And so it's interesting to understand transport physics, and one of the tools that we've used in the last few years as part of this synergy project that Jairo mentioned at the beginning, is to use electron spin resonance spectroscopy to understand the spin relaxation behavior of these polymeric system, and then relate the spin dynamics to the charge dynamics. And so I want to show you an experiment now where we have basically made a field effect transistor with such a conjugated polymer system, and then use that FET to, we basically put this FET into an ESR cavity, and then measure the ESR spectrum as a function of gate voltage on the FET. As you switch on the device, you can see here the increase in current as a function of gate voltage. And so as you increase the gate voltage, you induce more and more charge carriers in the organic system. And here you can see how the line shape of the ESR, the signal strength of the ESR signal increases as we increase the gate voltage. And so this allows us to in a sense, measure the spin properties or spin relaxation properties of these charge carriers that we induce with the gate as a function of carrier concentration and as a function of temperature. And so from the line shape, the line width, and the lines that the line widths, how the light shape saturates with microwave power in an ESR experiment, you can extract the spin relaxation times T1 and T2 in these systems. And here you can see a summary plot of the spin lifetimes T1 is in blue here, the top line, and then in orange is T2. And you can see this characteristic behavior. T1, as you go from low temperature to high temperature, T1 decreases monotonously from quite long values of hundreds of microseconds at low temperatures to still, well, moderate values at room temperature. So at room temperature, the spin relaxation time is on the order of 100 nanoseconds. And then T2 has a more complicated temperature dependence, where you initially see this regime where T2 decreases with increasing temperature. So that's a regime where essentially the charges are hopping from side to side slowly, and so they have enough time for the spin to dephase. I mean, when they're sitting on a particular site, they see a local magnetic field orientation, which is determined by the combination of the external field and also the hyperfine fields that the charge sees locally. And then the spin processes around these local magnetic fields. And if they're hopping slowly, that process becomes the spin dephasing becomes more effective as at higher temperatures, as the charges hop faster to sites that have a different local field orientation. But then around 50 Kelvin, you see this characteristic turnover where the spin relaxation time T2 starts to increase again. And that's a regime that some of you will be familiar with. It's a motional narrowing regime. As the charges move faster and faster, they start to average more effectively over the local magnetic field environments. And these fluctuations in the local fields are less able to dephase the spin. And so you have then a regime where spin relaxation becomes less and less effective as the charges move faster and faster. And we can use, in fact, this regime, as you can analyze that quite quantitatively and basically determine quantitatively hopping frequencies from the characteristic timescales for field fluctuations. And so we estimate, for example, that at 150 Kelvin, the hopping basically happens with a typical frequency of about 1 gigahertz in this system. And then you can use the measured mobility values to also estimate hopping length, and the values you get are on the order of 20 nanometers. So that's close to the length of a chain. So we know from these measurements that we can say quantitatively that charges are hopping in these polymeric systems with a roughly tens of nanometers every nanosecond. At around 150 Kelvin, the T2 goes through a maximum here, and then it decreases again as we go towards room temperature. So clearly at 150 Kelvin, this motional narrowing regime stops and something else is kicking in. And this something else took us a while to figure out what happens there. It's not expected. We had expected the motional narrowing to become more and more effective as we increase the temperature, because the charges are moving faster and faster in these polymeric systems. The mobility, carrier mobility in this polymer system is thermally activated, so transport becomes more and more effective towards room temperature. But still, that's not what happens with the spin relaxation. And it turns out that the reason why spin relaxation the spin relaxation time goes down again towards room temperature is because the spins start to couple very strongly to the structural dynamics. As you go towards room temperature, also in a polymeric system, you have these large vibrational motions, and in particular you have to think about the torsional vibrations of the ring systems in the polymer chain against each other. So there are thermally excited torsional vibrations. And what these do, they do something very similar to what's happening in the molecular systems. I explained at the beginning this surfing motion of the charge carriers on the waves of molecular lattice distortion that's relevant for the molecular systems. And in the polymeric system, something similar happens. These torsional vibrations of the backbone, they drive the carrier wave functions to oscillate periodically along the polymer backbone. And kind of locally, the structural vibrations, they drive an oscillation of the carrier wave function. And we think that this rapid oscillation of the wave functions is responsible for the spin relaxation. It's a mechanism that's probably similar to the what's called the Elliott-Jaffe mechanism for spin relaxation, where essentially normally people think of that in momentum space, that as electrons, Bloch electrons with particular wave vectors scatter at defects and change their wave vector, there is always a small probability that when this happens, the spin of the electron flips, and that's the so-called Elliott-Jaffe spin relaxation mechanism that's very well studied in inorganic semiconductors. And we think that in these organic systems, we have a very similar mechanism, but not in momentum space, but in real space, that as the wave function of the electron oscillates rapidly along the backbone, driven by these structural vibrations, that is a small chance that every time it oscillates, there is a chance that the spin will flip. And together with Eric McNellis and Jairo Sinova's group, we've developed a quantitative, reasonably quantitative model for this mechanism that's in good agreement with the spin relaxation times that we see in this high temperature regime here. It explains why the spin relaxation time decreases with increasing temperature in this regime as the molecular vibrations become more and more important. So this is a very interesting observation, because it builds a link between the molecular systems that I talked about in the beginning and the polymeric systems. The physics of these systems is quite different when you just look at, for example, the temperature dependence of the mobility in a molecular system. As I explained at the beginning, we see this band-like temperature dependence of the mobility, where the mobility increases with decreasing temperature. In a polymeric system, because of the residual energetic disorder that we have, typically the mobilities are activated. So it's not clear by looking at temperature dependence of the mobility whether there are any similarities between molecular systems and polymers. But if you look at the spin relaxation behavior, which is in a sense a more local probe of the charge dynamics of these systems, you actually see quite a striking similarity. And if you look at these plots here on the right-hand side, the top one is T1 and T2 for a molecular, highly crystalline molecular semiconductor. And it also shows this peak in T2 around 100 Kelvin. And that's very similar to what we've seen in the polymeric system. And so the reason for that, we think, is this close coupling between the structural dynamics driving these oscillations in the carrier wave function and that inducing spin relaxation. The mechanism for that seems to be very similar in molecular systems and in polymeric systems, and it allows us to understand a bit better how the physics of transport in these two systems is related. So with that, I've come to the end of the talk. I want to spend a few minutes acknowledging the people who've been involved in this work. Sorry, my clock is telling me I should shut up. So the people who've been mainly involved in this work, Guillaume Schweicher, he's done most of the work understanding the transient localization in molecular systems, together with Michael Ruggiero, who did the terahertz spectroscopy. And we worked closely with Gabriele Davino and Simone Frattini in Grenoble to develop the transport theory of that. And then in the polymeric system, I want to particularly acknowledge Sam Schott, who did all the ESR experiments, Angela Wittmann, who worked on the spin pumping experiments that I showed. And then on the theory side, Eric McNellis here in Mainz and in Jairo Sinova's group. as well as Vincent Lemour and Johan Olivier in David Beljon's group at the University of Mons, also on the theory. And then, of course, as I said in the beginning, we rely heavily on friendships with chemists who provide us with these interesting molecules. And for this talk, I want to particularly acknowledge Cameron Jellett at Imperial College in the group of Ian McCullough. And with that, I want to thank you very much for your attention. I'm very happy to answer any questions.
Thank you very, very much for your very nice clear talk. Let's see, if you guys would like to ask some questions, please, okay. Let me allow, just put up your hand up and I will give you the microphone. Let me see, allow, so submit. I think you are now, should be able to ask a question. Yeah, go ahead.
Can you hear me?
Yeah, we can hear you.
So thank you for the nice talk. Could you comment on the nature of spin orbit coupling in this molecular crystal? Because the way we understand this thing, this new spin orbit coupling comes from the crystal symmetry, which again relies on the fact that the structure is solid and not changing in time. But in your case, it can have some vibrational mode or different layer can slide on each other. So does it give some new phenomena regarding spin orbit coupling?
That's a very, very good question. I mean, we've been trying to quantify the strength of spin orbit coupling in this system, and maybe skipped a little bit the details here for this mechanism of this Elliott-Derford spatial scattering that we think is responsible for the spin relaxation near room temperature. That mechanism, of course, depends, is proportional to the strength of the what we call the spinnet mixture, which is a measure of the strength of the spin orbit coupling. So this parameter gamma that you see in this equation here, you can see here the results of a calculation of this spinnet mixture depending on the conformation that these molecules have in the solid. You get a distribution of spinnet mixtures and distribution of spin orbit coupling. So the spin orbit coupling is quite sensitive, for example, to the other to the molecular orientation, molecular torsion. So it's not just dependent on the chemical composition. It's, of course, the chemical composition, you don't have any heavy atoms in these systems, so the spin orbit coupling tends to be relatively weak, but it does depend a lot on the molecular conformation. I don't know, Eric and Jairo, do you want to comment on this?
Yeah, I mean, I think the big part of this is trying to calculate which has not been done before, this spin-up mixture parameter, which depends a lot, by the way, on many factors, particularly on the angles of between the molecules and the vibrations of the moles themselves. Not so much. We haven't studied that because essentially you effectively do it perturbatively, where the spin-orbit coupling and together with the phonons coupled together with this admixture to give you that. But in this, we do have the nice thing that there's some scaling that we observe with the different molecules. And that's the thing that we have tested thoroughly in a couple of works that we reported on. But yeah, it's not very strong, unfortunately. So you don't have manipulation as the other system.
You asked whether there are new phenomena induced by spin orbit coupling. I'm not sure that.
I wouldn't say it's just more complex, because I think we do know the ingredients. It's not new ingredients to the phenomena. Is that that here is a little more hidden by the disorder that you have on the system. That's very good to research. So Paul, can you go ahead and unmute yourself and ask the question?
Sure.
Yeah, thank you for the nice talk, Henning. I had a question about your model where electrons are surfing on these lattice modes, if that also predicts the occurrence of bipolar rods. You know, it's an old team in the field.
Yes. I don't know whether I don't know whether the theoreticians have looked at that. I mean, for those in the audience who are not familiar with bipolar ones, it's essentially a state where two charges are attracted to each other by sharing a molecular lattice distortion. These charges tend to be polaronic, so they are surrounded by a distortion of the molecular lattice, and by sharing that, there's at high charge densities, there is an attractive interaction that makes these charges form bipolar one states. I don't know, Paul. I haven't thought about it. I've seen Jochen Blumberger in the audience. Jochen, do you want to maybe comment on this?
I have to give him the
oh
the way to. I can allow him to talk.
I might put him on the spot.
That's okay, Jochen. I think I allow you to.
Jochen understands much more about this than I do.
Jochen,
I think that's very, very interesting suggestions for future research. I think I personally, we haven't looked at this, and I think it's very complicated because one has to get a handle on describing basically the interaction between charge carriers. So transient localization theory, the way how it's derived, I mean, it's always, you never really consider the interaction between different charge carriers. So that's always sort of at an infinite dilution limit, if you like. But yeah, it's a very interesting question, probably a very tough problem, I think.
Okay.
But it should, I mean, I would have thought it should be the right framework to use. Certainly in a molecular system, that's the right physics to start with if you want to understand whether bipolar ones do form or but as you say, Jochen, it's complicated.
Okay, well, maybe we see it in a future conference, hopefully.
Yes.
You know, in SPICE conference.
Yeah.
Or SPICE conference.
Yeah, exactly. Okay, thank you.
Okay, Matthias, go ahead and unmute yourself and ask a question.
Yeah, thanks, Henning. I have a very basic question, might just show my ignorance of the field. You've showed two different methods to learn something about spin in these organic systems. You looked at the spin pumping for the small molecules and ESR for the longer polymeric systems. Now, I mean, of course, you could theoretically do both for both, and I'm sure there must be some reason why you do one for the other and not the other.
Well, maybe it's probably that's my fault. I should have made that much clearer. This last results that I showed, they were both field-induced ESR measurements, not done by us. The top result is for a molecular system investigated by Jun Takeya's group in Tokyo, but it's a field-induced ESR measurement, essentially the same experiment that we have done for the polymeric systems. So they are more or less directly comparable, and they show very similar behavior, which is something that surprised me because I hadn't expected that systems that supposedly have so different physics end up having spin relaxation times that are very similar. They're both 100 nanoseconds, around 100 nanoseconds at room temperature, and have also very similar temperature dependence. Yeah, so these are both ESR measurements. The spin pumping measurements that Angela did, they provide, of course, somewhat complementary and different information.
And if you take the lifetime from the ESR measurements plus the diffusion constant, do you get the spin diffusion length that are measured by spin pumping?
That's a little bit complicated because it's probably quite anisotropic. In Angela's measurement, we're measuring the spin diffusion into the film. So typically these organic molecules are oriented with their long axis parallel to the normal of the substrate. And so in the spin pumping geometry, you have spin diffusion essentially across the layers, which is the low mobility direction. Whereas in ESR, what we're probably probing is the spin diffusion in the plane as molecules from molecule to molecule. So it's not directly comparable.
Okay, that makes sense. Thanks.
Okay, Julius, go ahead and ask your question, please.
You have shown quite nicely how the presence of this saturated alkyl substituents killed the mobility. You mentioned few reasons for that. I wonder whether you thought or perhaps tried to sort of coupled double bonds of carotene that would give you few advantages. Firstly, you most probably would have a coupling of your aromatic part with this coupled diene part, so you would have a higher delocalization.
Yes.
Secondly, you would shift your vibrational density of states to higher frequencies.
Yes.
And thirdly, you most probably reduced this cone movement of the saturated tails, most probably to a 2D plane, as far as I could envisage it. Have you thought about that?
Yes, that's a very good idea, and it's been a long-standing dream in a sense for people to have access to molecular systems like that, and synthetically they're not so easy to make. But we've had recently access to a system which Ian McCullough's group had made, which essentially has no single bonds along the backbone. It's essentially just a double bonded. I mean, it looks a bit similar to these fused ring system. I mean, maybe I should go to a different slide. If you look at this system here, our favorite IDTBT system has this fused ring structure, but then it still has single bonds along the main chain. And we've recently, through collaboration with Ian, we've had access to a system where these single bonds are replaced by double bonds, not in this system, but in a similar system. And you're right, it does enhance the electronic coupling between neighboring molecular units significantly. And that's a good thing. But it also introduces a stronger sensitivity to residual disorder as soon as you have some torsional disorder, because in the solid state there's always some torsional disorder present. You become more sensitive to that because the units are coupled more strongly together, and so those two effects you have to balance. And so far we haven't really managed to develop these double bonded systems. I mean, they work very well, but not as well as we had hoped. And I think that's because you have to be even more careful about eliminating torsional disorder in these systems to achieve low degrees of energetic disorder. But it's certainly a very interesting future direction that we would like to explore more.
Thank you.
Excellent. So I think that was the last question so far today. I think Angela, by the way, Angela is here in the panels. Angela, are you still there? Or yeah.
Hi, yeah.
Yeah, yes. So she's in Mainz soon. Yeah. We've managed to recruit Angela, aka Vanessa. You remember this? Yeah, a whole day calling you that, and then at the end of the day, Henning says, "By the way, her name is Angela." Anyway, okay, so I think I'm going to shut down the live streaming. Hang on for a second.
Yes, thank you so much for your attention. Real pleasure for